that it has already been recorded. Don't be in that state. You start writing whatever I am writing.
Okay, sir.
Hmm. So this is a matrix multiplication, right? This is one matrix, 3 cross 2. This is 2 cross 1. So multiplying is not a problem. The number of columns of the first one and number of rows of the second one are same. So how do you multiply these two matrices? How do you multiply? Yeah, how do you multiply?
So from first row to first column, I mean, we select the first row of the first matrix and then we multiply it with the first column of the second
Yeah.
matrix.
So that is what is exactly known as inner product. That is what is exactly known as inner product. So so one row from here and the column from here. That is how it is, isn't it? So it is something like uh, 1 comma 3 or inner product or uh, yeah, inner product x1 comma x2. So that gives you, and similarly 1 comma 2 x1 comma x2, 0 comma 1 uh, x1 comma x2. That's how it is, right? So this gives you uh, so this gives you, sorry, this gives you a matrix x1 plus 3x2, x1 plus 2x2, and x2. That's right. This is how the matrix are multiplied. This is how, this is what we have been seeing all these days. Let me put it in another way. Let me put it in another way. Uh, so this matrix A x, this is A for us, this is x. So A times x, let me write it in this way, x1 times 1 1 0 plus x2 times 3 2 1. Is there any problem with this? So what it results? It results in x1 times 1, x1 times 1, 0 plus 3x2, 2x2, x2. This is equal to x1 plus 3x2, x1 plus 2x2, x2. Both are same, right? I didn't do anything great here. I have simply uh, done the matrix multiplication in a different way. So This is one way, this upper part is one way, and this one is another way. What exactly I am doing here on the upper part? I am utilizing the rows. So rows are being utilized of the first matrix, and here columns are being utilized. Rows of first matrix and columns of first matrix, sorry, columns of first matrix. Okay, so where do we start? Where we started? We started with ax equal to b. So then I told you that we will talk about ax. So let us first understand what exactly ax means. In order to understand ax is nothing but multiplication of two matrices. But then our understanding regarding multiplication of two matrices is with respect to rows of first matrix or columns of first matrix. So rows of first matrix, this is how we have been doing while writing programs, while multiplying two matrices. This is how we have been doing, right? For so many years, we have been doing. Let us do it in this way and try to understand what exactly it means. Okay? Both of them give the same result. Is there any question till now? No question?
No.
That's okay. Okay. So, what is this exactly? The second one. First one I did not tell you. The second one. The second one is this one is a vector. Let me say vector A1, which has been scaled x1 times. That's right. This is another vector, vector A2, which has been scaled x2 times. x1 is a scalar quantity, a1 is a vector quantity, x2 is a scalar quantity, a2 is a vector quantity. x1 and x2, they are the scalars and they scale a1 and a2 respectively. So let me write it in this way: a1 times x1 plus a2 times x2. This is exactly we are doing. While multiplying two matrices, this is exactly we are doing. So what exactly this is? If you recall yesterday's class, you have one vector a1, one vector a1, another vector a2. I'm sorry. Another vector a2. This a1 and a2 I have scaled x1 times. This a1 and a2 I have scaled x1 times and x2 times respectively. Then their addition. This is what has been done, isn't it? So what this thought actually leads to? This is one column. let me say this one as a column. Sorry. Column A1, and this is column A2. Sometimes it is called as vector, sometimes it is known as column. So column A1. So what exactly this A1 x1 plus A2 x2 mean? A1 x1, A1 x1 that is now scaled. Let us say this is A1 x1. And let us say this is scaled A2 x2. So sum of these two leads to a space, or in this case it would be an area. Sum of these two would lie somewhere here. That's right. So this leads to an idea of column space. So this column space is nothing but combination of all columns where these columns are given by A1 and A2, and these columns are scaled by some real number x1 and x2. Okay. So now with the real number x1 and x2, we have infinite possibilities of AX. And this can be visualized geometrically. That's right. Now, um, but then I made a mistake here. The mistake is A1 is not limited to two-dimensional space because there are three elements. So let me add one more there, one more. Okay. So A1 is a vector or a column in the three-dimensional space because it has three values, right? It has got three values. So A2 is a vector in three-dimensional space. So this three-dimensional space A1 x1 and this A2 x2, they give rise to another space. So this entire space we called it as R3, space of real numbers. Now the question is, the combination of A1 x1 plus A2 x2 is a subset of R3. Is that right? Let me
Yes,
write
sir.
it again. This entire space is called as R3. R3 is the R indicates real number, and there are three vectors on this R3. These are the three vectors. These are the three vectors, and these three vectors denote the entire three-dimensional space. Now this A1 x1 plus A2 x2 is a subset of R3. Can you tell me what this shape would be? What would be the shape of this?
Sir, parallelogram.
Well, it will be a parallelogram, or to be
Plane.
very precise, it will be a plane. To be very precise, it will be a plane. It will be a plane. Now, what I should do, so that this plane becomes a space? What should be done so that this plane becomes a space?
If another
Sir,
dimension is added to it.
Another vector added to it.
introduction of a vector perpendicular to this plane.
Yes, another vector if I add, then there is a possibility that this may become a space. So the another vector would look like a1 x1 plus a2 x2 plus a3 x3. That's right. So if this corresponds to a space that is equal to R3, there is a possibility of this. If I add a3 x3, there is a possibility. But then, first of all, we understood what is column space, right? The space between these two vectors, a1 and a2. Now here in this case, x1 I have taken in this direction. Sorry, x1 I have multiplied with a1 and I have extended it to up to here. Up to here I have extended, right? There is a okay. I told you that x1 is also a real number, so it could go on this direction also, isn't it? It's a negative number. It can go on this direction as well. This can also go in this direction also. And this is the origin, let us say. Now, so the plane is this. This entire is a plane. So this entire one is the plane that this a1 x1 plus a2 x2 tells. So it's a plane bounded by two vectors a1 and a2. This is your a2, starts from here to here, bounded by a1. This is from here to here. So with respect, when you multiply x1, this has got infinite possibilities. When you multiply x2, this a2 has got infinite possibilities. So with all those possibilities, this plane is created. Now, if you say x1 is equal to 0, x2 is equal to 0, this plane reduces to a point, and that point is nothing but the origin. That's right. If you say x1 is some non-zero quantity and x2 is 0, so this plane becomes a line. This plane becomes a line. x2 is 0, x1 is non-zero. Also to say x1 is 0, x2 is non-zero. So this plane becomes a line. Now the next question is, in what way we can make it space? So I need to add another vector a3. Another vector a3. Now the question is, if a3 lie on the plane, if a3 lie on the plane, will it make a space? Will it make a space?
No, sir.
No, sir.
So if a3 is on a1 x1 plus a2 x2, or if I say if a3 is on the column space, if a3 is on the column space of a1 and a2, then it still remains a plane.
Sir, you write something on lower side of board?
Lower side of board means
You something right?
I'll something right means what? Complete the sentence, please.
Sir, you are something right on the board.
Sir, actually, is asking.
Sir,
I mean, in this, we don't know the. If we scroll back, it will enlarge and zoom on the whiteboard. So he just needs to scroll back.
No, no, I didn't get it.
Actually, sir, this whiteboard in its when we see your writing in this whiteboard, we only see the part of the whiteboard, not the whole whiteboard, right?
Yes.
So yes, to see the whole whiteboard, we need to scroll back with our mouse.
Yes.
You can zoom out.
Acha, I
You can
can
zoom
zoom
in,
out.
zoom out. So there is option for everyone.
It will be too small to visualize.
No, sir, we can zoom out on our side. No, you don't need
Sir,
to.
we can do by ourselves, but he don't know. That's why he is asking the question.
He's asking the question.
Ah, ha, ha. So you can hold your mouse and do that.
Sir, okay.
Okay. I mean, scroll your mouse. The that will zoom in, zoom out. There is an option here too. You can. So this is again, this whiteboard is again bounded by two vectors, which is infinite possibilities, limited to the memory actually. So I can drag it anywhere. So that is how this AX stands. Okay. Okay. So what is the takeaway from this? The takeaway is the column space of A fill the column space of A. How do I write this? The column space of A is filled by the combination of the columns. To be very precise, it is actually linear combination of columns. Sorry, I am sorry. The column space of A is filled by the linear combination of columns. I'm writing here. Linear combination of the columns. So this is nothing but the column space of A is filled by the linear combination of columns. This is what is the understanding of this entire thing. Here so many keywords are there. Please understand these keywords. What is column? What do you mean by column space? Now you understand what exactly the linear combination means, what is filled, and so forth. With this, if there is any question, please ask. With this, we complete this AX. It's simple a matrix multiplication. The meaning is very big. I just wanted to convey the meaning. So those who joined late, little bit let me tell you in brief. We started with AX equal to B. We try to understand AX equal to B, but first we try to understand AX, then we'll come to this B part. We took two matrices, A and X, with all conformity of matrix multiplication. Number of rows here, number of columns here are same. This is one way of multiplying. That is what is generally known as inner product. This is one vector, 1, 3. This is another vector, 1, x1, y, x1, x2. So two vectors are multiplied here, or inner product is there. So the inner product, yeah, if you do not know what exactly inner product is, this is again something new for you. The same thing what you have been doing, that is what exactly the inner product is. So, or to be very thing like this is something like sum of what do you say, AI, BI. So I equal to 1 to n. This is what your inner product is. Yeah, this is what your inner product is with two vectors AI and BI. I ranging from 1 to n. So n dimensional vectors, two n dimensional vectors inner product is this. This one is the two n dimensional inner product. The same thing I have been doing here. So this is what we call as, generally we know it as a row multiplication. Then this, sorry, okay. Then I told you about this columns. Instead of taking the rows, I took first column multiplied by first element of x, second plus second column multiplied by second element of x. So that is what I have been doing. And finally, it gives you the same result. But then we are in the objective of understanding AX. So A comprises two vectors, A1 and A2. A1 is scaled by x1, scalar quantity. A2 is scaled by another scalar quantity x2. That is why they are known as scalar. They scale. They scale. So x2. So this vector A1, A2 is also known as columns because they are columns, right? In A matrix, they are columns. So they are also known as columns. So let me write it as column A1, column A2. So now this column A1, I made it column A1 here and column A2 here. I scaled it by x1 as because x1 is a real quantity from negative infinity to positive infinity. This vector may extend in this direction. Similarly, A2 may extend in this direction. So depending on the value of x1 and x2, this entire plane is filled. So this entire plane is known as the column space. Or so to say, column space is the combination of all columns. So these are the two columns. They are linear combination. So These blue vectors, they create the space R3. Now this linear combination A1 x1 plus A2 x2, they create a subset of R3 that is known as the plane. What do I do if this plane has to be a space? I will be adding another vector, A3. But whether all A3 are permissible, let us take one A3 that lie on the plane. So if A3 lie on the plane, then A1 x1 plus A2 x2 will still be the same. Just A3 x3 is a part of the space. A3 is nothing but the part of the original column space of A1, A2. So it doesn't add anything. The column space of A1, A1 then still remains as a plane. So A3 has to be something different from A1, A1, A1 and A2. What is that different? A3 has to be A3 has to be independent of A1 and A2. Then only we will get a space.
Sir,
Mhm.
sir, if we are increasing another column in matrix A, then we also increase another row in X matrix, right?
That is X3 I have written. No?
So in A3 has to be independent of A1, A2, and then X3 will also be independent of X1 and X2.
Well, X1 and X2 are the scalar quantities. So X1 can be 1, X2 can also be 1, X3 can also be 1. So they are the scalar quantities, so it is immaterial.
Okay.
So for example, X1 is 0, X2 is 0. So this entire plane reduces to a vector, reduces to a point, that is origin. So in this case, X1 is 0, X2 is 0. Both are same. Understood? So the takeaway
Yes.
is the column space of A is filled by the linear combination of the columns. That is why linear, the word linear. We'll talk about this linear in another class. It actually will take one full class to understand what exactly the meaning of linear is. Okay, let us come to the second part, that is B. This B. AX equal to B. Now the second part, AX equal to B. This complete part. So what is B? Let me write it in this way. B is also a vector, right? B is also a vector. So B is in the column space of A. Let me write column space of A as this. B is in the column space of A when AX equal to B has a solution x1, x2. We are still in 2 dimension, okay? A is I mean, there are only 2 columns in A. We are yet to add A3. A1 and A2 are the 2 columns. So B, it is the same thing what you have been learning. B is in the column space of A when AX equal to B has a solution x1 and x2. Or in other words, the solution X, this solution X, it shows how to express the right side of B. This x1, x2 tells you how to express B. As a linear combination of the columns A1 and A2. Let us say B is B1, B2. Let us say B equal to B1, B2. So this B or B1, B2 will be expressed by a linear combination of A1, A2 with X1, X2. If this satisfies, then only this entire thing holds. So okay, so let us say what value did I take there? Let me take a vector like yeah. So finally, let me take let me consider this one, x1 plus 3x2 B is equal to let us say 1, yeah, B is equal to, this will be too small, x1 plus, just a second, let me write it here, x1 plus 3x2, x1 plus 2x2, x2. Okay, done. So we have, yeah, that's it. Okay, let us start this. Let us take B is equal to 1, 1, 1. Let me take B is equal to 1, 1, 1. So we have AX. What is AX? AX is equal to, we have already calculated AX, x1 plus 3x2, and then x1 plus 2x2, x2. Can this be equal to B? Is it possible? Is this correct?
No, sir. No, sir.
Why?
Sir, sir, after solving first and second, we are getting x2 equal to 0.
But x2 is equal to 1 here.
Yeah.
The third line, third row, it says x2 is equal to 0. But if you solve these two, you get x2 is equal to, sorry, the third line says x2 is equal to 1. But solving these two, you get x2 is equal to 0. Or in other words, if I replace x2 is equal to 1 here in the first equation, so this becomes 3 plus x1 is equal to 1. So x1 is equal to 1 minus 3, that is equal to minus 2. So x1 is equal to minus 2. X1 is equal to minus 2 plus 2. So x2 becomes, here it should have been 0. So this does not hold. So this does not hold. Right? What does it mean? What does it mean? It means B is not in the column space of A. So this B, this is not in column space of A. That is what this objective of this entire equation is. You need to find such a kind of B. You need to find such a kind of X such that B will be inside the column space of A. So the solution x1, x2 has to be in such a way that B is inside the column space of A. Or so to say, B has to be expressed in such a way that this x1, x2 becomes a solution of the column space A in whatever language you tell. It is the same thing. So,
Sir,
yes,
sir, when you say column space that you explained previously that a plane, right? In A1, X1, and A2, X2. So,
that's
sir,
right.
what does the B significance? That B is the point that lies outside the plane, or what?
B is another vector that lies inside the column space. The combination of linear combination of columns, that is the column space. So B has to lie inside this.
I mean, in this example, this is not lying in the column space.
This is not lying in the column
Uh,
space.
and the sir, when you said the linear combination with what, sir? I mean, A matrix has the linear combination with X variables, right?
That's right.
And then what will be the linear combination of B?
Why do you need a B? I mean, linear combination of B.
So you said na that B is a column vector. So to create a column vector, we need a variable uh, such as x1, x2.
Why?
So you said na B is column vector just right
Yeah,
now.
B is also a vector that is expressed as, here I am expressing it as a 1, 1, 1.
Okay. Then sir, what does the B signifies? That vector part only.
Yeah. Let me rephrase your question. Don't ask that what B signifies. Let us ask what AX equal to B signifies. Okay. So in order to understand this, we understood what is AX, right? AX declares a column space. AX defines a column space. That is the linear combination of the columns of A scaled by X. Now, equal to B, equal to B. This means that B is inside the column space defined by this AX. The right hand side is inside the column space defined by the left hand side. And that is what I write. B is in the column space of A when Ax equal to B has a solution x1, x2. Or in other words, you modify this the same sentence in a different way. Like um, you need to express B. Mm, how to, you need to express B the right side, as a combination of A1 and A2 with x1 and x2. You need to express, let me write it here. So unit, this is one way of expressing, this is one way of telling the same thing. This is another way of telling the same thing. Two different ways. The meanings are same. Let us say in a very simplified way, ax equal to b, solve for x. Now it is given, ax is given, find out what is b. The b has infinite possibilities again. That is what is given here. Express the right hand side b as a combination ax1, a1 x1 plus a2 x2.
Okay, sir. So then the B is any vector that lies in that plane of AX.
Exactly. That is what the thing is.
Okay, okay.
Sir,
Okay. Yes.
sir, but for the given x1 and x2, we have a so we have a plane limited by x1 and x2. We can have more than one b's within the space.
Yes, of course. That's right. Like here, in this example, b doesn't conform. This vector doesn't lie on the plane, and we have this particular plane. We have this particular plane. In this plane, there are so many here. A3, one example I have taken. There could be anything. There could be any vector. Infinite possibilities are there. They lie on this plane, B. They lie on this combination of column space, A1 and A2.
Hello, sir.
Yes.
So then for every B which lies in the column space, we need to find the corresponding scaling factor, no, sir, x1 and x2.
Of course, yes. It is another way of telling the same thing. Yeah.
Yeah, I got that point. Okay, thank you, sir.
So that means as the vectors are constant, that is A1 and A2 are constant, that means B varies with x1 and x2, right?
B, no. No. B cannot vary with x1 and x2. B has to lie inside A1 x1 plus A2 x2. Yeah, you can say they are dependent on x1 and x2. Because let us say x1 and x2 equal to 0, 0. So the column space of A1, A2 reduces to a point. Now you have a vector B equal to 1, 2, 3. So that doesn't lie. So in that way, you can say yes, x1 and x2 are to some extent dependent on B. They will tell. Yes, that's right.
And so one more thing, this B vector originates from origin, right?
Okay, in that way, now let us go back to our previous class, physics. In physics, whenever we define vector, it doesn't originate from the origin. But in linear algebra, mostly we start from the origin. We start from the origin. So that is what the liberty we have in the linear algebra. So A1 originates from origin, A2 originates from origin. But if you recall, has your physics teacher, did your physics teacher tell from where it originates? It actually, they were silent about that. My teacher was also silent about that. I don't know your teacher. Did he tell you?
No, sir. He just randomly draw any vector or 2D
Yeah.
domain.
So there actually we were means the with respect to the world space. The world space is not defined, but that's a vector. That's a vector. That's how we know it. It's a magnitude and a direction. So defining everything starting from the origin, it gives a very clear understanding of the entire concept. So it's already beyond 10 o'clock. You might have the second class, next class. So if you have any question, we will, take up in the next class. Okay. Thank you. Thank you, everybody.
Thank you, sir.